To enhance soil conductivity for ground rods and achieve a resistance of 25 ohms or less, several methods can be employed. These methods involve modifying the soil, using multiple rods, applying chemical treatments, managing soil moisture, removing obstacles, and considering different grounding techniques. Firstly, soil amendments can significantly improve conductivity. Bentonite clay enhances soil moisture retention and ion exchange capacity. Gypsum or calcium sulfate converts heavy clay soils into a more porous and conductive state. Ground limestone or lime can increase the pH, which in some cases can improve soil conductivity. Secondly, installing multiple ground rods creates multiple conductive pathways. Driving additional ground rods at different depths and spacings can lower the overall resistance. Consider using a new for ground, which consists of multiple rods connected to a metal grid embedded in the foundation. Thirdly, chemical treatments can be used with caution to improve soil conductivity. Copper sulfate can provide a temporary improvement, but it is toxic and requires careful handling. Electrolytes, such as salt or baking soda, can be added to the soil to enhance conductivity. Fourthly, improving soil moisture can make a significant difference. Watering the soil around the ground rods regularly can enhance conductivity. Installing a drip irrigation system helps maintain consistent soil moisture levels. Fifthly, removing obstacles ensures that the ground rods have optimal contact with the soil. Ensure that the ground rods are not installed near metal objects or underground utilities, as these can interfere with their conductivity. Clear away any rocks or debris that may inhibit contact between the rods and the soil. Consider different grounding methods depending on the soil conditions. Driven ground rods are typically more effective in sandy or rocky soils. Bare ground plates are suitable for areas with poor soil conductivity or limited space. Chemical grounding uses chemicals to create a conductive layer in the soil. Electrolytic grounding introduces a conductive solution into the soil to enhance conductivity. Before installation, test the soil conductivity to determine the soil's resistivity and decide on the appropriate grounding method and number of rods required. Use high-quality ground rods made of copper-clad steel or stainless steel for durability and corrosion resistance. Ensure proper connection by using a grounding clamp to securely connect the ground rods to the grounding system. Regularly inspect and test the grounding system to ensure it remains within the required resistance levels. The effectiveness of these methods may vary depending on specific soil conditions. Consult with a qualified electrician or grounding expert for specific recommendations and proper installation. Electrical grounding is a critical safety measure designed to protect people and equipment from electrical shock and damage. It works by providing a low resistance path for fault current to flow back to the source, tripping the circuit breaker or fuse and energizing the circuit. Grounding systems typically consist of a grounding electrode, such as a ground rod or ground plate, which is connected to the earth, and a grounding conductor, which connects the electrode to the electrical system. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems to ensure safety and effectiveness. Grounding serves several important purposes. Firstly, it protects against electrical shock by providing a path for fault current to flow back to the source, stripping the overcurrent protection device. Secondly, it prevents the buildup of static electricity, which can damage sensitive electronic equipment. Thirdly, it stabilizes voltage levels in the electrical system, reducing the risk of voltage fluctuations. Fourthly, it provides a reference point for voltage measurements, ensuring accurate readings. There are several types of grounding systems, each designed for specific applications. Firstly, the grounded system has one conductor, typically the neutral, intentionally connected to ground. Secondly, the ungrounded system does not have any conductor intentionally connected to ground. Thirdly, the equipment grounding system connects the metal parts of electrical equipment to ground, providing a path for fault current. Fourthly, the separately derived system, such as a generator or transformer, requires its own grounding system. Selecting the appropriate grounding electrode is crucial for effective grounding. Firstly, ground rods are commonly used and are driven into the earth to provide a low resistance connection. Secondly, ground plates are buried horizontally and are suitable for areas with limited space or poor soil conductivity. Thirdly, concrete encased electrodes, also known as UFA grounds, are embedded in the concrete foundation of a building. Fourthly, ground rings are continuous conductors encircling a building and buried in the earth. Proper installation of ground rods is essential for their effectiveness. Firstly, drive the ground rod vertically into the earth until its top is below the surface. Secondly, space multiple ground rods at least twice their length apart to avoid overlapping their areas of influence. Thirdly, use a ground rod driver to ensure the rod is driven straight and deep into the soil. Fourthly, protect the top of the ground rod from damage by using a ground rod cap. Connecting the grounding conductor to the ground rod requires a secure and corrosion-resistant connection. Firstly, use a grounding clamp specifically designed for connecting grounding conductors to ground rods. Secondly, ensure the clamp is made of a material compatible with both the ground rod and the grounding conductor to prevent galvanic corrosion. Thirdly, tighten the clamp securely to provide a low-resistance connection. Fourthly, protect the connection from moisture and corrosion by applying a corrosion inhibitor. Testing the grounding system is crucial to verify its effectiveness and ensure it meets code requirements. Firstly, use a ground resistance tester to measure the resistance of the grounding system. Secondly, perform the test under normal operating conditions to ensure accurate readings. Thirdly, compare the measured resistance to the code requirements and take corrective action if necessary. Fourthly, document the test results and keep them on file for future reference. Maintaining the grounding system is essential to ensure its long-term effectiveness. Firstly, inspect the grounding system regularly for signs of corrosion, damage, or loose connections. Secondly, repair or replace any damaged components promptly. Thirdly, retest the grounding system periodically to verify its continued effectiveness. Fourthly, keep the area around the ground rods clear of obstructions to ensure easy access for inspection and maintenance. Grounding requirements vary depending on the type of electrical system and the application. Firstly, the NEC provides detailed requirements for grounding electrical systems in buildings. Secondly, industrial facilities may have additional grounding requirements to protect sensitive equipment. Thirdly, telecommunications systems require specialized grounding to prevent interference and protect equipment. Fourthly, healthcare facilities have stringent grounding requirements to ensure patient safety. Understanding grounding principles is essential for anyone working with electrical systems. Firstly, grounding provides a low resistance path for fault current, protecting people and equipment. Secondly, proper grounding reduces the risk of electrical shock, fire, and equipment damage. Thirdly, grounding is a critical component of electrical safety and should be taken seriously. Fourthly, always consult with a qualified electrician or grounding expert for specific recommendations and proper installation. The 2023 National Electrical Code, or NEC, Section 250 covers grounding and bonding requirements for electrical systems. Grounding and bonding are crucial for electrical safety, protecting people and equipment from electrical shock and fire hazards. Section 250.4 outlines the general requirements for grounded systems, ensuring that they are grounded in a manner that limits the voltage to ground and facilitates the operation of overcurrent protective devices. Section 250.4b covers ungrounded systems, requiring them to be equipped with ground detectors to provide an indication of a ground fault. Section 250.20 specifies the systems that are required to be grounded, including alternating current, or AC, systems operating at 50 volts or more, and direct current, or DC, systems operating at certain voltage levels. Section 250.24 details the requirements for grounding electrode systems, which must consist of one or more grounding electrodes that are bonded together to form a low-impedance ground bath. Acceptable grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. Section 250.50 outlines the requirements for the grounding electrode conductor, which connects the grounding electrode system to the system grounded conductor. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the largest ungrounded conductor. Section 250.52 specifies the requirements for grounding electrodes, including their installation and minimum size. Ground rods must be at least 8 feet long and driven at least 8 feet into the ground. Ground plates must have a surface area of at least 2 square feet. Section 250.53 details the requirements for the installation of grounding electrodes, ensuring that they are installed in a manner that provides a reliable and effective ground connection. Ground rods must be driven at least 8 feet apart and ground plates must be buried at least 30 inches below the surface. Section 250.64 outlines the requirements for the bonding of electrical equipment, ensuring that all metal parts of electrical equipment are bonded together to create a low-impedance ground path. Bonding conductors must be sized according to NEC Table 250.122, based on the rating of the overcurrent protective device. Section 250.92 specifies the requirements for bonding service equipment, ensuring that all metal parts of service equipment are bonded together to create a low-impedance ground path. Service equipment includes the service disconnecting means, the service overcurrent protective device, and the meter enclosure. Section 250.96 details the requirements for bonding metal water piping systems, ensuring that they are bonded to the electrical system to prevent electrical shock hazards. Metal water piping systems can become energized if they come into contact with a live electrical conductor. Section 250.104 outlines the requirements for bonding other metal piping systems and exposed structural metal, ensuring that they are bonded to the electrical system to prevent electrical shock hazards. Other metal piping systems include gas piping, compressed air piping, and sprinkler piping. Section 250.118 specifies the types of equipment grounding conductors that are permitted for use in electrical systems, including wire-type equipment grounding conductors, rigid metal conduit, intermediate metal conduit, and electrical metallic tubing. Section 250.122 details the requirements for sizing equipment grounding conductors, based on the rating of the overcurrent protective device. Equipment grounding conductors must be sized according to NEC Table 250.122. Section 250.130 outlines the requirements for equipment grounding conductor connections, ensuring that they are made in a manner that provides a reliable and effective ground connection. Equipment grounding conductor connections must be made with listed connectors or by other approved means. Section 250.134 specifies the requirements for equipment grounding of cord and plug connected equipment, ensuring that the equipment is grounded through the grounding pin of the attachment plug. Cord and plug connected equipment must be grounded unless it is double insulated. Section 250.146 details the requirements for connecting the equipment grounding conductor to receptacles, ensuring that the receptacle is grounded through the grounding terminal. Receptacles must be grounded unless they are GFCI protected. Ground fault circuit interrupters, or GFCIs, are required in certain locations such as bathrooms, kitchens, and outdoor areas. GFCIs protect against electrical shock by detecting ground faults and interrupting the circuit. Section 250.166 outlines the requirements for grounding separately derived systems such as generators and transformers, ensuring that they are grounded in a manner that limits the voltage to ground and facilitates the operation of overcurrent protective devices. Separately derived systems must have their own grounding electrode system. Understanding and complying with NEC Section 250 is crucial for ensuring electrical safety and protecting people and equipment from electrical hazards. Always consult with a qualified electrician or electrical engineer to ensure that electrical systems are properly grounded and bonded in accordance with the NEC. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer for specific recommendations and proper installation. Soil resistivity is a measure of how much the soil resists the flow of electrical current. It is an important factor to consider when designing grounding systems because it affects the effectiveness of the grounding electrode. Soil with high resistivity will require a larger or more elaborate grounding system to achieve the desired resistance to ground. Factors that affect soil resistivity include soil type, moisture content, temperature, and salt content. Clay soils generally have lower resistivity than sandy soils. Moist soils have lower resistivity than dry soils. Warm soils have lower resistivity than cold soils. Soils with high salt content have lower resistivity than soils with low salt content. Measuring soil resistivity is essential for designing effective grounding systems. Several methods can be used to measure soil resistivity, including the Wenner 4-electrode method and the Schlumberger array method. These methods involve driving electrodes into the ground and measuring the resistance between them. The measured resistance can then be used to calculate the soil resistivity. The Wenner 4-electrode method is a commonly used method for measuring soil resistivity. It involves driving 4 electrodes into the ground in a straight line, equally spaced apart. A current is passed between the outer 2 electrodes, and the voltage is measured between the inner 2 electrodes. The soil resistivity can then be calculated using the following formula: ρ equals 2 pi r, where ρ is the soil resistivity in ohm meters, is the spacing between the electrodes in meters, and r is the measured resistance in ohms. The Schlumberger array method is another method for measuring soil resistivity. It involves driving 4 electrodes into the ground in a straight line, with the inner 2 electrodes spaced closer together than the outer 2 electrodes. A current is passed between the outer 2 electrodes, and the voltage is measured between the inner 2 electrodes. The soil resistivity can then be calculated using a more complex formula. The choice of method depends on the specific application and the desired accuracy. Soil resistivity values typically range from 1 ohm meter to 1000 ohm meters. Low resistivity soils, such as clay soils, have values less than 100 ohm meters. Medium resistivity soils, such as sandy soils, have values between 100 ohm meters and 500 ohm meters. High resistivity soils, such as rocky soils, have values greater than 500 ohm meters. When designing grounding systems, it is important to consider the soil resistivity and to select a grounding electrode that is appropriate for the soil conditions. In high resistivity soils, it may be necessary to use multiple ground rods or a ground grid to achieve the desired resistance to ground. It may also be necessary to use soil amendments to reduce the soil resistivity. Soil amendments are materials that are added to the soil to improve its conductivity. Common soil amendments include bentonite clay, gypsum, and calcium chloride. Bentonite clay is a highly absorbent clay that can help to retain moisture in the soil. Gypsum is a calcium sulfate mineral that can help to improve the drainage of clay soils. Calcium chloride is a salt that can help to increase the conductivity of the soil. When selecting soil amendments, it is important to consider the soil type and the specific requirements of the grounding system. It is also important to follow the manufacturer's instructions for application. In addition to soil resistivity, other factors that can affect the effectiveness of grounding systems include the depth of the grounding electrode, the size of the grounding electrode, and the type of connection between the grounding electrode and the grounding conductor. The depth of the grounding electrode should be sufficient to reach a stable layer of soil with low resistivity. The size of the grounding electrode should be large enough to provide a low resistance path to ground. The connection between the grounding electrode and the grounding conductor should be secure and corrosion resistant. Proper grounding is essential for electrical safety. By understanding the factors that affect grounding system performance and by following proper installation and maintenance procedures, it is possible to ensure that electrical systems are properly grounded and that people and equipment are protected from electrical hazards. Always consult with a qualified electrician or electrical engineer for specific recommendations and proper installation. The information provided here is for general guidance only and should not be considered as substitute for professional advice. Always consult with a qualified electrician or electrical engineer for specific recommendations and proper installation.